about that. Anyway, I don't remember if I prayed today. I'll pray now just to be safe. Heavenly Father, we thank you for this day. Again, I thank you for this class and for this time we have to meet and study your creation. Just guide our steps as we're beginning to look at multilinear algebra and dual spaces and all this stuff, Lord. In your name I pray, Lord Jesus. Amen. All right, so yeah, let's get into it. So this is roughly based on my 2015 Advanced Calc notes. This is, chapter 9, which is essentially on multilinear algebra. And so in particular, with a focus on tensors, obviously, and algebra, the wedge product and all that. But at the start of everything, we should talk about the dual space. So given, V, which is, let's say, the span of E1, E2, En, right? So let's say it's a finite dimensional for our purposes here. We define V dual equals to, alpha, let's say, such that V goes to the reals, alpha linear. And so we're gonna focus. I don't think there's anything I really need. Maybe I'll regret this at some point, but I think we're just going to keep it real in this chapter. If we come to a point, all right, where we feel like we need something complex, we will then rethink our life and ask questions about whether or not anything here we could have done actually with another choice of base field. And honestly, as I think about the future, it's probably true we could just use complex numbers everywhere we're using reals, but I'm gonna just stay real. Okay, so the dual, in other words, it's the set of linear maps, right, from V to the reals. So these are called linear functionals, right? So example 1, if we have V equals to Rn, right? Then if we look at alpha of x, right? Well, that is what? That is, how's that go? Well, that's alpha of what? The sum I, xi, ei. I may soon start to have to caring about the location of indices here. Yeah, okay, I'm going to start caring. So I'm going to start imposing the convention that we write the coordinates up like this in order to, well, you'll see. Okay, so starting now, like that. Now, so this, by linearity, would be the sum over I equals 1 to n, right? Of what? Of, well, alpha of ei, right? xi. But you see, you could just as well write this as like alpha vector dotted with x as a vector, right? And where that vector is what? It's literally alpha of E1, alpha of E2, alpha of En, all right? So in this sense, there's an obvious correspondence between, vectors And something in V dual is called a dual vector. So this alpha, not the alpha vector, but this alpha is called a dual vector. Alpha, an element of V dual, is called a dual vector. All right, so in Rn, we could always just play this kind of silly game, all right? Now, theorem, if beta equals to E1 through En is basis for V, then B dual, which we'll use the notation E upper 1, E upper n, is basis for V dual defined by, well, let me say it this way. If that, then let E upper I on E lower j equal to Kronecker delta ij define this, which is a basis for V dual, called the dual basis. Dual basis to beta. So beta star is the dual basis of beta. Moreover, phi beta is equal to E1, E2, dot, 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 En. That is E upper I of x is equal to x upper I for all I. So it's a dual basis. And in fact, we can look at the dual basis as nothing more than the coordinate functions of the coordinate map for the beta. All right, so let's prove this. Okay, so if we let alpha be an element of V dual, right? Then let's see here. Alpha of x is equal to alpha of the sum over I of x upper I, E lower I, which is equal to the sum over I of x upper I alpha of EI. I really should have proved a lemma before I wrote this down, okay, but I'm just going to write it. And this is equal to the sum over I of alpha of EI, E upper I of x by lemma. Okay? Hence, alpha is equal to the sum of alpha of EI, EI, which is of course an element of the span of beta star.
Because EI maps every vector to its I coordinate.
Well, yeah, we need to prove that though, right? We should prove that.
Yeah.
So that's my lemma. So here's the lemma. Lemma is that E upper I of x is equal to x upper I if x is equal to the sum of xi EI. And the proof of it, so I say right here that that defines beta star. So what I'm using there is a result from linear algebra that if we define a linear map on the basis, there's a unique linear extension off the basis. So it should be clear, since I've defined the values of E upper I on the basis E lower j, we've defined that defines a linear map. So the linearity of the dual basis is by extension. It's essentially for free. I can define the values on the basis and extend linearly, so I do. That being said, the proof of the lemma is this: EI of x is equal to EI of the sum, I better use a different letter this time, j of x upper j, E lower j, but by linearity, the constructed linearity of the dual basis. And of course, if you don't like it, I could write down a formula for it and slog through the formula, but let's use linear algebra. Then we've got EI of EJ, right? But by construction, this is Kronecker delta IJ, the natural enemy of the finite sum, which leads us to just, all we have left there is x upper I. So that proves the lemma. Once we have that, that allows us to trade this for that, right? And then I noticed that all of this I can look at as, to be clear, I'm saying this is a mapping. And how do we define the sum of maps? Pointwise, right? So this map, x on x, and since this holds for all x, we have this equality. But then, of course, these are just numbers, and that's clearly in the span of the dual basis. Now, to prove it's a basis for the dual space, I have it to span, right?
Linear.
I need to check linear independence of beta star, right? So how can we prove linear independence?
Here in the proof of the lemma, you're saying that because the basis is linearly independent, then the linearity of the transformation.
Oh, no. I'm saying that the definition, I say define. What do I mean by that? I'm saying that essentially the definition, if you will, when I say define it by linearly extending off the basis, I'm literally saying the definition of this is that right there. This is the definition.
Okay.
That's the definition I'm talking about. That's the linear extension. I have not assumed yet that the dual basis is linearly independent. The basis is linearly independent.
No, I mean it's we know it's a linear transformation because the first basis is linearly independent, and we're linearly extending the basis.
Right. Yeah. Exactly. If we had the values on a set which was not linearly independent, it begs the question of single valuedness.
Mm-hmm.
Right. Yeah. That is true. So, linear independence of beta star, well, suppose that you've got the sum, right, over, let's say, C sub j of E upper j, and j equals 1 to n, and suppose that's equal to 0, right? Well, this is 0 in V star, right? So we're talking about the zero transformation. This is an operator. We can operate on a vector. May I suggest that we operate on, I don't know, E lower I, right? So this says that the sum, j equals 1 to n, of C sub j, E upper j of EI is equal to, 0 acting on EI, right? But this is Kronecker delta IJ by construction, by definition. And so this all simplifies down to CI. But on the other hand, 0 map on anything is 0. So we've just shown that the ith coordinate, the ith component, the ith, coefficient in this trivial combination is necessarily trivial. So the only trivial combination is the trivial The only combination which, adds to 0 is the trivial combination itself. Therefore, beta star is linearly independent. Aha! So we've actually just proved something more, haven't we? What did we just prove? Therefore what?
It is linearly independent.
What do we have about the dimension of V is equal?
It's the same.
Yeah, it's the same, right? So V, and V is finite dimensional, okay? As I warned you previously, if we're in infinite dimensions, you have to get rid of some of the linear functionals. There's too many. But okay, so for finite dimensions, we have this. So the dimension of V is the dimension of V dual. So once you do this once, then you want to do it again, so you can talk about V double dual. So I think you've studied these things before, yes?
I
A little bit.
homework problems in this.
Oh, okay, cool.
And the ones I submitted.
Oh, I'm sorry. I will eventually read your homework problems. But you already worked some problems. That's good. So V double dual, this would be linear maps from V dual to the reals, right? Now, the isomorphism that I just found, right, between V and its dual, it was, based on a choice of coordinates, right? It was not what we would call a canonical. If you can find an isomorphism between two objects which doesn't use coordinates, then that's an example of like a canonical isomorphism. And such is possible for V double dual here. And so here's the typical notation. So we do something like this, like V hat, all right? All right. V hat of alpha is going to be equal to alpha of V for all V and V, alpha in V dual. In other words, you can define the mapping psi, a mapping from V to its double dual, all right, by psi of V equals to V hat, where V hat is above defined like such. Now you can check that this is in fact a an isomorphism. Well, I mean, it's an isomorphism because you can just apply what we just did before, right? We know that a space is a finite dimensional vector space is isomorphic to its dual space, and since the double dual is the dual of the dual, right? So we have V is isomorphic to V dual, and we have that V dual is isomorphic to V double dual. So by transitivity of isomorphism, of course, we do know that V is isomorphic to V double dual. But on the other hand, we also have this canonical isomorphism, namely the hat. So this allows us to take. So when I think of a vector in a given vector space V, I sometimes don't think of it as an active object. I think of it as a passive object. It's just sitting there at points in a certain direction, right? But this viewpoint means that we can think of vectors as operators on dual vectors, is what this means. And that's a viewpoint we typically take advantage of. We allow ourselves to let vectors act on dual vectors. And how do we do that? A vector acts on a dual vector by letting the dual vector act on the vector. This is so stupid, but it works. And of course we can check that this is in fact, a linear transformation and all that jazz if you want. But you probably already did that homework.
I think so.
Yeah. All right, so, but you notice, again, there's no basis or anything going on here. It's just, that. Any questions?
Because alpha V, isn't that an element of V dual?
No, this is for alpha and V dual. So like alpha is a mapping
Yeah.
from V to the reals. So alpha of V is equal to a, is an element of the reals.
Yeah.
V hat should be a mapping from where? From V dual to the reals, right?
Yeah.
And so I'm producing a real number, like I should.
Yeah, because we had this function about.
We got it? Cool. All right, so, I guess I'm the last claim in my theorem in the previous board that it was the coordinate function of the coordinate map. I guess that's just obvious, right? From the formula, because if we have, EI of x is x upper I, well, that is exactly the ith coordinate of x in our notation. So, I guess another point here would be that I guess it's just a remark. I don't know if I thought about this before, but it occurs to me now that if we if we talk about beta has dual basis beta dual, right? Then beta dual has dual basis. I'm going to call it beta hat, right? Because I think, I bet you that it's this, right? Let's see if that's not the case. How would we check this? So beta dual has got what? It's E upper 1, E upper 2, E upper n, right? And then, so I'm imposing a notational scheme here, which is that when you dualize, you flip the indices again. But anyway, so the point is, if I have my, let me just introduce a temporary notation. Beta, the dual of the dual basis. Let's suppose that that's got f1, f2, fn, right? What defines these? Well, the defining condition is that fi of ej is equal to what? Kronecker delta ij, right? Now, sometimes I try to keep the indices straight on the Kronecker deltas. I just can't do it. Some people do. Some people have meanings for, anyway, listen, there's a lot of index conventions out there. And I can only go so far. All right, so anyway, so there's that. And, but on the other hand, this has a definition, right? Like E hat sub I, when it acts on EJ, how does that work? Or E upper J, right? We define the canonical isomorphism to be what? EJ acts on what? EI, right? But that's this. And since we have agreement of Fi and E hat I on a basis, it follows that Fi is exactly E hat I. So my remark is legit. So the dual of the dual basis is the canonical morph. It's the canonical morphed basis, the hat basis. Now, as we go on in here, I'm not actually going to put hats on things. You just have to understand from context whether or not we're thinking about a vector as an active object or a passive object. Your main clue is that if the vector is acting on a dual vector, I'm probably thinking of it as an active object. You know, if I'm operating on something, I'm probably thinking of it as an operator. You know, it's kind of a dumb comment, but it's relevant.
So the vector as an active object is the vector in the dual.
Yeah, technically.
Okay.
But these are isomorphic, so it's,
Yeah.
yeah. But it is an isomorphism we're going to exploit.
And what's the advantage of doing the active versus? Is it?
Well, it allows us to freely interchange the roles of V and V double dual. I mean V and V dual. Making V active puts it on the same footing in some sense as like V dual. That's one advantage. It's kind of like obvious. Otherwise, I would have to be introducing like the double dual and like distinguishing between the dual and the double dual in tons of places, and it would get old very quickly. All right, so next up, that's a dual vector. We got these. Now, so just to give you a snapshot of where we're going, I told you this before the camera was on, but to say it again now. Chapter 9 is on algebra. We're just going to do multilinear algebra. Then what we do in chapter 10 is we specialize all of these things to the case that the vector space is the tangent space to the manifold and the dual space is the cotangent space to the manifold. And then we're going to look at vector fields and differential form fields, and all of this stuff will come to life with the joy of multilinear calculus. And then we'll eventually get back to like reinterpreting the Fauché derivative in light of all these new constructions, because the Fauché derivative as we had it before was just a mapping, was literally a mapping inside a vector space. So we're going to elevate it to be like a mapping on tangent spaces or something. We're going to get there eventually. So there's some change of viewpoints as we go on, but anyway, that's getting ahead of the story. So at the moment we have dual space. Next up we start talking about what are called bilinear maps. So let's do that. What's a bilinear map? So definition, V1, V2 vector spaces over R, then B, a mapping from V1 cross V2 to the reals, all right, is a bilinear mapping on the Cartesian product of V1 and V2 if and only if it's linear in each slot. So number one, we need B of like Cx plus y on z is like C B of x comma z plus B of y comma z, and 2 B of x comma C z plus w is equal to like B of x, well C B of x comma z plus B of x comma w, and that's for all x and y in V1 and z and w in V2 and c in the reals. Now, I'm intentionally being probably more general than we usually are. Oftentimes we have the case that V1 is equal to V2. Okay, so if V1 is equal to V2, if V1 equals to V2, then B is bilinear, and let's say that these are equal to V, okay? It's bilinear on V, okay? Moreover, if B is bilinear on V and B of x comma y is equal to B of y comma x, or B of x comma y is equal to minus B of y comma x for all x and y in V, then fill in the blank, then fill in the blank. What do we got here? So if we can commute the inputs, then B is symmetric. Or to be the more full statement in all of its glory is B is a symmetric bilinear form. Doesn't that sounds very impressive, doesn't it? And if we have this anti-commuting condition here, then we say B is an anti-symmetric bilinear form. All right, so I just wanted to get that out in front of us right at the start. Now let's see what we can say in general about bilinear forms. What can we say? Check it out. So let's do a calculation. So B of x comma y is equal to B of the sum over I of x sub I e I, and then the sum over j, let's say, of y sub j. We'll use f sub j here because I'm trying to be a good citizen here and think of v1 and v2 being different. It's about the same trouble to derive it in the case that v1 and v2 are distinct, so why don't we do that? Admittedly, in the context that v1 and v2 take on the role of like dual spaces, I may impose certain dual space specific index placement conventions. I think that happens. But for the moment, we're just kind of ignoring those conventions in this general. Listen, those conventions are easy enough to adapt to when we come to them. So let's just leave it at that. So if it's bilinear, I can pull the summations out, right? So sum I equals 1 to n1, sum j equals 1 to n2, where of course I'm saying that, the dimension of v1 is n1, the dimension of v2 is n2. Okay, great. And we've got ourselves an x upper I, a y upper j, and then we got ourselves b, e, I, f, j. All right, wonderful. Now what? Well, hey, we just did something, right? We can look at this, and we can rewrite this, in fact, as the sum over I equals 1 to n1, and the sum j equals 1 to n2 of what? B, E, I, F, j of, well, that's really EI of x, and that's F upper j of y, is it not? By my lemma, or the theorem, depending which you want to look at. And so, yeah. So this leads us to make a definition. See, because if we just define this to be EI tensor, Fj, which we're going to define in a second here more carefully, but that's going to be, a mapping on V1 cross V2 to the reals. Well, that's, to be fair, define it by this, okay? EI tensor fj of x comma y, well, guess what it's going to be equal to? It is going to be equal to, this is really, yeah, EI of x and not even comma, just times fj of y. This is literally a multiplication of numbers. Now, question, why is that? Why is it? Now, I really need a name. Do I have a name in my notes? I got no name. I really need a name, but I have no name in our current context. But anyway, if this did have a name, if the set of all bilinear maps on V1 cross V2, if it had a name, right? For the purposes of this conversation, let us say that B is an element of this thing, okay? The set of all bilinear maps on V1 to V2, okay? I guess I should adorn this with a V1, V2 to be more fancy. So suppose that's just for the current conversation's sake. The set of all bilinear maps on V1 to V2. Well, it's fairly clear from this formula that EI tensor Fj is an element of the set of all bilinear maps on V1 to V2. Why is that? Well, it's manifestly clear from that formula. You can see it by looking at the formula that it's linear in the first slot and it's linear in the second slot. Why? Because the dual vectors are by construction linear and the formula, right? Like I break up a sum here, I multiply. I break up a sum here, I multiply. So by distributive property of real numbers, I have the bilinearity. So, okay, so what does this all mean? So this is actually equal to the sum over I, sum over j, right? And I got myself a B of EI, Fj, EI tensor Fj. All of this thing acts on what? It acts on xy. Where again, I'm using the definition that how do we add maps, how do we add functions together? Right? A bilinear map is at the base of everything a function. We already know how to define the sum of functions. I don't need to redefine that every time we invent a new kind of function. Right? Like some people, if they're sufficiently pedantic, will now make a separate definition on how do you add bilinear maps. Like, I'm not going to do that. We already know how to add functions. This is a function. This is how we add them. So, what does this mean? Well, that holds for all x and y. Therefore, you see this actually, this thing, right? It's actually the span of these guys. In other words, I am, a linear independence calculation away from proving that the tensor product of the dual basis is in fact itself a basis for the set of bilinear maps. Yeah? And how would that linear independence argument go? Let's do it, yeah? Now, linear independence for something that's double indexed, it's much better suited, like, yes, I mean technically a basis is an ordered basis. It has to be an ordered set of vectors, right? But in practice, no one actually enumerates them. We just say, oh, okay, so maybe use lexicographical ordering or something, whatever. It's not kind of the point. I mean, you could do that, but I would just like to do it like this. Cij of EI tensor F upper j, and I've got, j equals 1 to n2, and my I is 1 to n1, right? I set that equal to 0. Of course, this is 0 in this space, right? It's 0 as a mapping, technically a mapping from where? From V1 cross V2 to the reals. And then what am I going to do to get that my ijth component coefficient has to be 0? What do you do? this is true for all possible pairs of vectors. How can I, which pair should I use to suit my purposes? What should I feed it? What do you think?
We're trying to show the linearity.
We're trying to show linear independence of this set, EI tensor Fj, such that, this right here, such that 1 less than or equal to I less than or equal to n1, 1 less than or equal to j less than or equal to n2. I would like to argue that the thing in curly brackets is in fact a basis for the set of bilinear maps in V1 to V2. So just pick some other letters, right? Like take this and let it act on. Let me not rewrite that, okay? Let me not rewrite that. Let's just let it act on the pair, what? Maybe E sub, I need K maybe? F sub L perhaps? And then when it does it, we just, the calculation again, right? So that brings us to this, which becomes what? Like that, right? But what are those? By construction, those are Kronecker delta IK and Kronecker delta JL. And so we just get C KL. The K and L survive. The I and J are dummy indices of summation here. But K and L are arbitrary. Therefore, we have proved that a linear combination being 0 forces all of the coefficients to be 0. Consequently, as advertised, this is in fact a basis. And so we have the, basically proved the following theorem, which is that if V1 has dual basis beta 1 star and V2 has dual basis beta 2 star, right? Then the set of bilinear maps on V1 to V2, right, has basis, let's say beta 1 star tensor beta 2 star. And I'm defining the tensor symbol for my convenience here. I'm not saying that's something that people typically do. In fact, I don't know, that may not be standard notation, but I want to say, what I want to say is that this thing I wrote over here is what I would like to call beta 1 star tensor beta 2 star, if that makes sense. And so what does that then tell us? What's the dimension? What's the dimension of the set of bilinear forms? Can you tell me?
N1 times N2.
Yeah, n1 times n2, which more interestingly we could write as the dimension of V1 times the dimension of V2. All right. So, of course, we can specialize this in the case that we're just talking about, a bilinear mapping on the V. Then instead of having like the F's and the E's, we just have E's. Now, I give an example in the notes, which is freed from all this stuff. Let's see here, that's a good example. We should look at it. Well, I give two examples actually. So let's see here. We're on example, what, 3? So example 3 is simply this: b of x comma y equals to x dot y. Example 4 is b of x comma y equals to x transpose ay. Now here, in both examples, x and y are elements of Rn. So I'm defining a bilinear form on Rn. All right? A bilinear form on Rn. So here again, bilinear forms on Rn. Here A is an element, it's an n by n, a square matrix, okay? Now we can easily check that, of course you know that the dot product satisfies bilinearity. That's like week 1 in Calc 3, right? This we know. And really, example 4 is example 1, right? Because you could rewrite this as x transpose the identity matrix times y. So really they're not different examples, truth be told. And, so b of like x1 plus cx2 or something like that, comma y, would be x1 plus cx2. We transpose that thing times ay, which would be like x1 transpose ay plus c times x2 transpose ay, which of course would be b of x1y plus c b of x2y. So there you go. There's like proof of the bilinearity in the first slot, but we can do these things. Now, let's see here. So I defined the tensor product of two dual vectors for the purpose of my previous theorem, but I should stop and define that more generally. Definition: if alpha and beta are elements of V dual, then alpha tensor beta is a mapping from V cross V to the reals, right? And how do we define it? And again, okay, fine. So like in my proof of the previous thing, I indicated that you can just as well take I don't have to have alpha and beta from the same dual space even, right? I can still meaningfully define the tensor product of two dual vectors even if they're from different dual spaces. But here I'm just...
It would be alpha of x times alpha, beta of y.
Right, yeah. And you can easily prove that alpha tensor beta is a bilinear form. Okay? Now here's an interesting question. And this is not an easy question, I think, in general. All right? So here's something for you to chew on. Given, B, a bilinear mapping from V to V cross V to the reals, right? Does there exist, right, alpha and beta in V dual such that what? Such that B is equal to, alpha tensor beta. So if you think about this problem, think about that question linear algebraically, you should be able to see that the answer must be no, generally speaking. Why? What did we just prove? We just proved that the set of all bilinear forms, right, is isomorphic to what? It's isomorphic to a vector space of dimension v1 times v2, right? Oh, but I guess there might be, maybe you could find it though. Oh yeah, that doesn't do it either, does it? It's not quite that. No, it's not so simple as that. Hmm. Hmm. I'm not going to answer the question. Like, I'm just saying that's the question that you can ask for a given bilinear form is, does there actually exist? I mean, it's possible. Obviously, it's clearly the case for the, for any, I mean, if B is an element of my, what I've called, B dual tensor B dual, right? That's definitely the case that it is, right? But, you could have other things, right? You could have something like B is equal to, oh, I don't know. You guys may like this, like E1 plus E2 tensor E1 tensor E1 and then like plus E1 minus E2 tensor E3, something like that, if you have like a three-dimensional space, for example. And so if you look at that, I'm pretty sure that this is not equal to alpha tensor beta for any choice of alpha and beta. But anyway, this is a harder question to think about. Now, so getting back to bilinearity, let's talk about bilinear maps on V a little bit more to hopefully conclude today. I've just got a little bit more to say. I'm almost done. So if we have a symmetric bilinear map, we're going to introduce the following notation, like, so B of xy, forget about the symmetric for a second, just a bilinear map on V. Then we've got what? We've got the sum over I and j equals 1 to n, and we've got ourselves, x upper I, y upper j, b of ei ej, right? Which of course we could rewrite as the sum, well, we're going to rewrite it like this, bij ei tensor ej acting on xy. So this is our definition, is b sub ij is going to be like b of ei ej in this kind of context. Okay? So every bilinear form corresponds in some sense to a matrix. All right? If B is symmetric, right? If B of xy is equal to B of yx, what's that say? That implies that bij is equal to bji for all ij, right? And so a symmetric bilinear form will have a symmetric matrix. Likewise, an anti-symmetric bilinear form will have, I think you can guess where this is going, an anti-symmetric matrix. Oops. Where of course we're thinking of like I as a row index and j as like a column index, I suppose. All right. Now there's a deeper conversation to be had here because there's like 4 different kinds of bilinear maps on V we could think about, quote unquote. We could think about like, what I'm trying to say is we could think about a bilinear map on like V cross V. We could think about a bilinear map on V cross V dual. We could think about a bilinear map on V dual cross V. We could think about a bilinear map on V dual cross V dual. Each one of those would have a different kind of matrix because it would be defined on the bilinear map on either pairs of dual vectors, vector dual vector, or dual vector dual vector. And if the coordinate change, if we thought about coordinate change for the dual basis, the properties, how these matrices would transform under a change of coordinate would be different for these different four scenarios. So we should get into that. We should talk about that, all right? But just for today, I just wanted to point out that if it's symmetric, it's got a symmetric matrix. If it's antisymmetric, it's got an antisymmetric matrix. The other really cool thing to notice is any bilinear form can be written as the sum of a symmetric and an antisymmetric bilinear form as follows. Check this out. So you just do this. 1/2 b of xy plus b of yx plus 1/2 b of xy minus b of yx. This is symmetric. This is antisymmetric. That shows that any bilinear form can be decomposed uniquely, in fact, into a sum of a symmetric and a antisymmetric bilinear form. Enjoy this. Appreciate it while it lasts, because this is the last time this happens ever. As you go to higher ranked tensors, like a trilinear map, or more generally a multilinear map, we can still look at completely symmetric or completely antisymmetric tensors, but it is no longer the case that a general tensor can be decomposed simply as the sum of a symmetric and an antisymmetric tensor. This is very special to bilinear maps. The story of how a tensor decomposes into irreducible, independent components, if you will, is the story of representation theory, which is beyond this course. But anyway, I should mention these things as we're going. So like next up, we're going to talk more about, maybe we'll talk more about the coordinate change issue for bilinear maps. Maybe I'll just go on and talk about trilinear and multilinear, and how we can build up multilinear maps from tensor products of dual vectors. There is another perspective which is more algebraic, which says that tensor products are formed by a formal quotient of the Cartesian product of like vector spaces. That's lovely, but we're interested in tensors as operators on spaces, so that more formal, admittedly beautiful algebraic construction doesn't really help us too much in here, and I'm going to avoid it. So, but of course the comments will be full of, why are you doing this? You could just use universal principles. Don't you know the category theory, blah, blah, blah. And I'm just ignoring those people. So, sorry people.